Hello everyone. Today we'll be continuing with our discussion about expectation of a random variable. So there is one important result which we will see now. We have seen how to compute expectation of x when x is a simple random variable or elementary or non-negative or arbitrary random variable. Now we will talk about expectation of function. So expectation of any function of a random variable is actually same as integral of that function with respect to the same probability measure which we use for the original random variable. Okay, so the important thing here is if you have a continuous random variable x, then expectation of gx would actually be integral gx into pdf into dx over entire r. Okay, and if you have discrete random variable, then expectation of gx would be sum over gx into probability that x is equal to x for all possible values of x. So s is support. So basically you can use pdf of x or pmf of x, which is same as this, that is the induced probability measure induced by x. You don't need something like dpgx, okay, or you don't need pdf of gx, or you don't need pmf of gx. Okay, you can simply use the pmf of x. This is also known as rule of a lazy statistician, because you don't have to compute distribution of gx. You can simply use distribution of x and still get expectation of gx. So this is very important. In fact, that's what we use while computing MGF, moment generating function, probability generating function, or even characteristic function. Okay. Another couple of important formula that we are going to see today. So suppose I have a discrete random variable which support say 0, 1, 2 up to infinity. So basically all non-negative integers is my support. Then we know that expectation of x can be defined as sum over x into probability of x equal to x, where x goes from 0 to infinity. Okay. So this, because when x is equal to 0, this term is going to be 0, I can write this as sum over x going from 1 to infinity, x into probability of x equal to x. Okay so far? Now let me write this in expanded form. So this becomes probability of x equal to 1 plus 2 times probability that x is equal to 2 plus 3 times probability that x is equal to 3 and so on. Okay, so we continue this way. Now what does this mean? Let me try to rearrange these terms a bit. So this becomes probability of x is equal to 1 plus this twice, let me write as probability of x is equal to 2 plus probability of x is equal to 2. The third term is thrice, so let me write as probability of x is equal to 3 plus probability of x is equal to 3 plus probability of x is equal to 3 and so on. Okay, so what is this? Let me focus on the first row. So first row is simply addition of probability of x equal to 1, x equal to 2, etc. So this is probability of x being greater than or equal to 1, the entire first row. Okay. Similarly, entire second row becomes probability of x being greater than or equal to 2. Entire third row becomes probability of x being greater than or equal to 3 and so on. Okay. So this means that expectation can actually be written as sum over probability of x greater than or equal to x, where x goes from 1 to infinity. Okay. It can also be written as sum over x going from 0 to infinity, probability of x strictly greater than x. Check. So probability of x strictly greater than 0 would mean probability of x greater than or equal to 1. Okay. And probability of x strictly greater than x can also be written as 1 minus probability of x being less than or equal to x. Okay. And probability of x less than or equal to x is nothing but the CDF. Okay. So this is same as sum over x going from 0 to infinity 1 minus CDF at x. Okay. So these are two important formulas. So either you can write this way or you can write this way. So these are two important expressions for expectation of x. Okay. Now let us try to see what would be the continuous equivalent of this. Okay. So in continuous case we can worry about two things separately. So one is if I have a non-negative random variable and other is if I have a random variable which takes negative as well as positive values. So let us try to see what would happen in the continuous case. So we should get something equivalent, right? So let me assume x is a continuous random variable with some PDF of x and support of x, let it be non-negative. So let it be 0 to infinity. Okay, support of x is 0 to infinity. Now in this situation my expectation of x becomes, it is exact equivalent of what we did in the summation here. So it becomes integral 0 to infinity 1 minus fx dx. Okay, so if x is always greater than or equal to 0. So if x is a non-negative random variable, then this is the form. So it is exact translation of this. The only difference is summation is being replaced by integral sign because we are in the continuous setup. If x is arbitrary, means if support of x is minus infinity to infinity or some subset of it, then in that case expectation of x becomes integral minus infinity to 0 CDF of x dx plus integral 0 to infinity 1 minus CDF of x dx. Okay, we have not done the discrete equivalent of this, so try that. Okay, try discrete equivalent of this, means if I have a discrete random variable which takes even negative values, then do we get formula for expectation in this form? Of course integrals would be replaced by summations. Okay, do try that. So now we have to start our discussion about characteristic function also. By the way, if you want to derive these two, these can be derived by using your formula for integration by parts. Okay, it's not difficult. So you can try that. So let me stop here. Thank you.